Close your eyes and imagine darkness. Not the darkness of a moonless night, where stars still pierce the sky. Not the darkness of a cave deep underground, where you could light a match and see again. Imagine true, absolute, eternal darkness. A darkness so complete that no light exists anywhere. No stars, no galaxies, no glowing embers of dying suns. Nothing but an infinite void stretching in all directions, forever. This is the eventual fate of our universe, not billions of years from now, not even trillions. But after an almost incomprehensible span of time, measured in numbers so large they strain human comprehension, the last star will flicker and die. After that final light fades, no new stars will ever form. The universe will enter an age of permanent darkness, continuing to exist, but unable to produce the light and energy that once filled it. This inevitable ending is written into the fundamental laws of physics. It's not a catastrophe we can prevent, or a disaster we can avoid. It's simply the natural conclusion of cosmic processes that began with the Big Bang nearly 14 billion years ago. But before we reach that ending, before the last star dies, the universe will pass through many ages. Stars will continue forming for trillions of years to come, far longer than the universe has currently existed. Galaxies will collide and merge. Black holes will consume matter and energy. And through it all, gradually, inexorably, the raw materials for making stars will be depleted. Understanding the last star requires understanding how stars form, how they die, and how the universe itself changes over cosmic timescales. We need to trace the entire stellar life cycle from beginning to end, and then extend our vision into a future so distant that the universe we know would be utterly transformed. Stars are not eternal. Every star that shines in our night sky will eventually die. Our sun, middle-aged and stable, has about 5 billion years of life remaining. Massive blue giants burn through their fuel in just millions of years. Small red dwarfs can persist for trillions of years, outlasting nearly everything else in the cosmos. But even the longest-lived stars are temporary. They shine by converting hydrogen into helium through nuclear fusion, releasing enormous energy in the process. This energy creates the pressure that holds the star up against gravity's inward pull. When the fuel runs out, fusion stops, pressure drops, and the star begins its death sequence. What happens next depends on the star's mass. Massive stars explode as supernovae, scattering their enriched material across space and sometimes leaving behind neutron stars or black holes. Medium stars like our sun swell into red giants, cast off their outer layers, and fade as white dwarfs. Small stars simply cool down over trillions of years, gradually dimming until they're dark, cold remnants. Each generation of stars creates heavier elements through fusion and supernova explosions. The first, stars contained only hydrogen and helium, the simplest elements created in the Big Bang. When those stars died, they scattered carbon, oxygen, iron, and other elements into space. Second-generation stars formed from this enriched material, creating even more heavy elements when they died. Our sun is a third or fourth generation star, born from the remains of previous stellar generations. The carbon in your body, the oxygen you breathe, the iron in your blood, all were created inside ancient stars that died before our solar system formed. We are, quite literally, made of stardust. This cycle of stellar birth, life, death, and rebirth has continued for nearly 14 billion years. But it cannot continue forever. Each cycle depletes the universe's supply of usable hydrogen. Each generation of stars locks some matter into remnants that can never form stars again. White dwarfs, neutron stars, black holes, these are stellar endpoints, objects that will never fuse hydrogen again. Over time, the available hydrogen diminishes. Star formation slows. The universe gradually transitions from a place bright with newly forming stars to a darker, quieter realm, where star formation becomes increasingly rare. Eventually, the last pocket of hydrogen capable of collapsing into a star will do so. That final collapse will create the last star that will ever exist. And when that star dies, no new stars will replace it. This is not immediate. The last star won't form for an almost unimaginable length of time. Current estimates suggest star formation will continue for 100 trillion years, perhaps longer. That's 7,000 times longer than the universe has currently existed. It's a span of time so vast that human minds struggle to conceptualize it. But it is finite. And after that final star forms and lives out its life cycle, the age of stars will end. The universe will enter what cosmologists call the degenerate era, a period lasting 10 to the power of 40 years, where white dwarfs and brown dwarfs are the primary remaining objects. After that comes the black hole era, lasting until 10 to the power of 100 years, where black holes slowly evaporate through Hawking radiation. And after that, the dark era, continuing essentially forever, where nothing remains but the faintest particles and the void. But we're getting ahead of ourselves. Before we can understand the last star, we need to understand the first stars, how stellar evolution works, and how the universe's supply of star-making material becomes depleted. Let's begin at the beginning, with the first light that ever shone in the cosmos. The universe was not always filled with stars. For hundreds of millions of years after the Big Bang, the cosmos was dark. Not the darkness of night, but the absolute darkness of a universe that had never known light. The Big Bang occurred approximately 13.8 billion years ago. In the first moments, the universe was unimaginably hot and dense, filled with pure energy. As it expanded, it cooled. After about 380,000 years, it had cooled enough for electrons and protons to combine into hydrogen atoms. This is called recombination, and it's when the cosmic microwave background radiation was released. After recombination, the universe consisted primarily of hydrogen gas with smaller amounts of helium and trace amounts of lithium. These elements, created in the Big Bang, were distributed almost uniformly throughout space. Almost, but not quite. Tiny density fluctuations, quantum variations stretched by cosmic inflation, created regions slightly denser than average. Gravity pulled these denser regions together. Gas clouds collapsed under their own weight, growing denser and denser. As they collapsed, they heated up. Eventually, some clouds became hot and dense enough in their cores to ignite nuclear fusion. The first stars were born. This happened somewhere between 100 and 400 million years after the Big Bang. Astronomers call this period cosmic dawn, the moment when the universe's first light sources ignited and began illuminating the primordial darkness. The first stars were unlike any stars we see today. They're called population 3 stars, and they were massive, hundreds of times the mass of our Sun. They burned incredibly hot and bright, with surface temperatures exceeding 100,000 degrees Celsius. They shone with a brilliant blue-white light that flooded their surroundings with ultraviolet radiation. These stars were short-lived. Despite their enormous size, or rather because of it, they consumed their fuel rapidly. The most massive might have lasted only a few million years before exhausting their hydrogen and dying in spectacular supernova explosions. When they exploded, they scattered the first heavy elements across space. Carbon, oxygen, silicon, iron, elements forged in their cores and in the violent conditions of the supernova itself, mixed with the primordial hydrogen and helium. Second-generation stars, population 2 stars, formed from this enriched material. These stars were smaller, cooler, longer-lived than their predecessors. They ranged from a few solar masses to hundreds of solar masses, but the average was lower than population 3 stars. Population 2 stars formed in greater numbers. As the universe aged, more and more stars ignited. They began clustering together, pulled by gravity into groups that would eventually become galaxies. Our Milky Way galaxy formed during this period, about 13 billion years ago. It began as a collection of population 2 stars and gas clouds, gradually organizing into a rotating disk with a dense central bulge. Other galaxies formed similarly throughout the universe. Over billions of years, population 2 stars lived and died. They created more heavy elements, further enriching the interstellar medium. Eventually, the concentration of heavy elements reached a point where a new generation of stars could form. Population Y stars, like our Sun. Population I stars are metal-rich, using the astronomical definition of metal as any element heavier than helium. They contain carbon, oxygen, iron, and other elements in significant quantities. This allows them to form with a wider range of masses, from tiny red dwarfs barely massive enough to fuse hydrogen, to blue supergiants hundreds of times more massive than the Sun. Our Sun formed about 4.6 billion years ago, from a collapsing cloud of gas and dust enriched by previous stellar generations. It's a thoroughly average population 1 star, neither particularly large nor particularly small, neither especially hot nor especially cool. The Sun will continue fusing hydrogen for another 5 billion years. Then it will exhaust its core hydrogen, swell into a red giant, and eventually cast off its outer layers, leaving behind a white dwarf that will cool for trillions of years. But the Sun is just one star among hundreds of billions in our galaxy, and one of trillions upon trillions in the observable universe. Star formation continues throughout the cosmos. New stars are born every day in stellar nurseries, vast clouds of gas and dust, where gravity pulls material together into dense cores that ignite fusion. The rate of star formation, however, has been declining for billions of years. The universe reached peak star formation about 10 billion years ago. Since then, the rate has steadily decreased as available hydrogen is consumed and locked into stars and stellar remnants. This decline will continue. Slowly at first, then more rapidly, the universe will exhaust its star-making fuel. We're currently in what you might call the late afternoon of the stelliferous era, the age when stars dominate the universe. The evening is coming, and after that, the long night. To understand why star formation must eventually cease, we need to understand the process by which stars form and the requirements for that process to occur. Stars form in molecular clouds, vast regions of space filled with cold gas and dust. These clouds can be hundreds of light years across and contain enough material to create thousands or even millions of stars. The Orion Nebula, one of the nearest star-forming regions to Earth, is giving birth to new stars right now, roughly 1,350 light-years away. Within these molecular clouds, the gas is not uniformly distributed. Turbulence, magnetic fields, and gravity create density variations. In some regions, the gas is denser than average. These denser regions exert stronger gravitational pull, attracting more material. If a dense region reaches critical mass, gravity overcomes the pressure and magnetic forces that resist collapse. The region begins contracting, pulling itself inward. As it contracts, it fragments into smaller clumps, each of which can potentially become a star. These collapsing clumps are called protostars. As a protostar contracts, gravitational potential energy converts to heat. The core temperature rises. Material continues falling inward, adding mass and heat. Eventually, if the protostar is massive enough, the core reaches about 10 million degrees Celsius. At this temperature, hydrogen nuclei have sufficient kinetic energy to overcome their electromagnetic repulsion and fuse together. 4 hydrogen nuclei combine to form one helium nucleus, releasing energy in the process. This is nuclear fusion, the process that powers stars. The energy released creates outward pressure that balances gravity's inward pull. The protostar stops collapsing and enters the main sequence phase, where it will spend most of its life steadily fusing hydrogen into helium. The minimum mass required to ignite hydrogen fusion is about 0.08 solar masses, or roughly 80 times the mass of Jupiter. Objects below this threshold are called brown dwarfs. They can fuse deuterium, a heavier isotope of hydrogen, but they cannot sustain hydrogen fusion. They gradually cool over billions of years, never truly becoming stars. The maximum mass for a stable star is less clearly defined but appears to be around 150 to 200 solar masses. Above this limit, the star's radiation pressure becomes so intense that it blows away its own outer layers, preventing further mass accumulation. Most stars form with masses between these extremes, following a distribution called the initial mass function. This distribution favors smaller stars. For every massive blue giant that forms, hundreds of small red dwarfs are created. Red dwarfs are the most common type of star in the universe. They have masses between 0.08 and 0.4 solar masses, burn their fuel incredibly slowly, and can persist for trillions of years. The smallest red dwarfs might live for 10 trillion years or more, nearly 1,000 times the current age of the universe. These long-lived red dwarfs will be important when we discuss the last star, because they'll be among the final stars still shining when star formation ceases. Now, let's discuss why star formation must eventually end. The process requires specific conditions: sufficient gas density, low enough temperature that the gas doesn't have too much kinetic energy to resist gravitational collapse, and minimal disruption from radiation or stellar winds. Crucially, it requires hydrogen. Stars fuse hydrogen into helium. Once hydrogen is gone, fusion stops or shifts to heavier elements, which requires higher temperatures and pressures. Most stars cannot achieve the conditions needed to fuse elements beyond helium. Only massive stars can fuse carbon, oxygen, and heavier elements. The universe's total hydrogen supply is finite. It was created in the Big Bang and has been slowly decreasing ever since through stellar fusion. Every star that forms locks some hydrogen into helium and heavier elements. Every stellar remnant, whether white dwarf, neutron star, or black hole, represents hydrogen that's been permanently removed from the star formation cycle. Additionally, not all hydrogen is available for star formation. Much of it exists in hot, ionized gas that's too diffuse and energetic to collapse. Some is locked in planetary atmospheres, moons, and other objects. Some has been expelled from galaxies by supernova explosions or active galactic nuclei. The fraction of the universe's hydrogen that's actually in cold molecular clouds, capable of forming stars, is relatively small and decreasing over time. Galaxies replenish their star-forming gas through several mechanisms. Gas from the intergalactic medium can fall into galaxies, providing fresh material. Supernova explosions can trigger new star formation by compressing nearby gas clouds. Stars themselves return some material to the interstellar medium through stellar winds and planetary nebulae. But these processes are insufficient to maintain star formation indefinitely. More hydrogen is consumed and locked away than is recycled back into usable form. The net trend is toward depletion. Moreover, the universe's expansion plays a role. As space expands, galaxies move apart. The density of the intergalactic medium decreases. Gas that might have fallen into galaxies billions of years ago is now too distant, carried away by cosmic expansion. Dark energy, the mysterious force accelerating cosmic expansion, makes this worse. The expansion rate is increasing. Distant gas clouds are accelerating away from galaxies faster than gravity can pull them in. This cuts off the supply of fresh material, leaving galaxies to subsist on their existing reserves. Over time, each galaxy's star-forming gas is depleted. Star formation slows, then stops. The galaxy enters a post-stellar phase where it consists of long-lived stars, stellar remnants, and planets, but no new stars are being born. Different galaxies will exhaust their star-forming gas at different times. Massive elliptical galaxies, which have already converted most of their gas into stars, might cease star formation relatively soon on cosmic timescales. Smaller spiral galaxies with larger gas reserves might continue for much longer, but eventually, all galaxies will run out. The entire universe will transition from the stelliferous era to the degenerate era. Current estimates suggest significant star formation will continue for roughly 100 trillion years. After that, star formation will become increasingly rare, limited to the occasional collision between brown dwarfs that briefly produces a red dwarf or other exotic events. The last conventional star, formed through the gravitational collapse of a gas cloud, will likely be a small red dwarf. It will ignite quietly in some distant galaxy, shine for trillions of years, and eventually fade into darkness, never to be replaced. That star will be the subject of our exploration as we move deeper into the cosmic future. We live in the stelliferous era, the age of stars. This era began with the first population 3 stars, roughly 100 to 400 million years after the Big Bang, and it will continue for roughly 100 trillion years into the future. To put that in perspective, the universe is currently 13.8 billion years old. The stelliferous era will last about 7,000 times longer than the universe has currently existed. We're in the early stages, the cosmic morning, of the age of stars. But even within the stelliferous era, there are distinct phases. The peak of star formation occurred about 10 billion years ago, roughly 3 billion years after the Big Bang. At that time, galaxies were forming stars at rates far exceeding what we observe today. The universe was brighter, more active, filled with young, hot, massive stars. Since then, the rate has declined. The Milky Way currently forms about 1 to 2 new stars per year. In the distant past, the rate was perhaps 10 times higher. In the distant future, it will drop to near zero. Let's trace what happens as the stelliferous era ages and eventually comes to its conclusion. In about 5 billion years, our Sun will exhaust its core hydrogen and begin its red giant phase. It will swell enormously, possibly engulfing Mercury and Venus, and certainly making Earth uninhabitable if life still exists here. After roughly 1 billion years as a red giant, the Sun will eject its outer layers as a planetary nebula and settle into a white dwarf that will cool for trillions of years. Other stars in our galaxy will follow similar paths according to their masses. Massive stars will explode as supernovae. Medium stars will become white dwarfs. Small red dwarfs will continue shining for trillions of years. In about 4 billion years, the Andromeda galaxy will collide with the Milky Way. Despite the word collision, actual stellar collisions will be rare because stars are tiny compared to the spaces between them. But the two galaxies' gravitational interaction will distort their shapes, trigger bursts of star formation as gas clouds collide, and eventually merge them into a single larger galaxy. Astronomers call this future galaxy Milkomeda or Milkdromeda. It will be a giant, elliptical galaxy containing hundreds of billions of stars from both predecessor galaxies. The collision will consume much of the remaining star-forming gas in both galaxies. A brief burst of intense star formation will occur as gas clouds compress and collapse, but afterward, the merged galaxy will have depleted much of its reserves. Star formation will slow dramatically. Similar mergers will occur throughout the universe. Galaxy groups and clusters will coalesce. Smaller galaxies will be absorbed by larger ones. Over time, the universe's galaxy count will decrease as mergers combine them into progressively larger structures. By about 100 billion years from now, cosmic expansion will have carried distant galaxies beyond our cosmic horizon. From Earth's perspective, or from whatever vantage point exists in the future Milkomeda galaxy, the rest of the universe will have disappeared. Distant galaxies will have accelerated away faster than their light can reach us. Future astronomers will observe only their own galaxy, surrounded by empty space. This is called the Big Isolation. Each galaxy cluster becomes an island universe, causally disconnected from all others. Information can no longer travel between them. They exist in separate, isolated bubbles of space that can never interact again. Within Milkomeda, star formation will continue, but at an ever-decreasing rate. By 1 trillion years from now, nearly all the massive and medium stars will have died. Only red dwarfs and brown dwarfs will remain, along with white dwarfs, neutron stars, black holes, and planets. The night sky, from any planet orbiting a red dwarf will be mostly dark. No brilliant blue giants. No glowing nebulae where new stars are forming. Just the faint red light of cooling red dwarfs, growing dimmer each passing millennium. At 10 trillion years, star formation will have essentially ceased in Milky and similar galaxies. Occasional events might produce short-lived stars. Brown dwarfs might collide, combining their mass to exceed the fusion threshold and create a small red dwarf. White dwarfs might accrete matter from a companion star and reignite briefly. But these are rare temporary events. The last conventional star, formed through the gravitational collapse of a molecular cloud, will have long since been born. It will be a small red dwarf, perhaps 0.1 solar masses, shining dimly in the deep red portion of the spectrum. This star will continue fusing hydrogen for trillions of years. Unlike massive stars that race through their fuel supplies in millions of years, red dwarfs are miserly with their resources. They convect efficiently, mixing their entire volume so that all their hydrogen can participate in fusion. A typical red dwarf might last 10 trillion years on the main sequence. Some estimates suggest the smallest ones could persist for 20 or even 30 trillion years. During this time, they'll gradually dim as their internal composition changes and their fusion rate decreases. Eventually, even the most frugal red dwarf will exhaust its hydrogen. Fusion will stop. The star will contract slightly, heat briefly through gravitational contraction, then begin cooling. Unlike larger stars, red dwarfs don't swell into red giants or eject planetary nebulae. They simply fade. The star will transition from a red dwarf to a blue dwarf, a theoretical stage that occurs only in very low-mass stars. As it contracts, its surface temperature actually increases slightly, shifting its color from red to blue. But this phase is brief and dim. After the blue dwarf phase, the star becomes a white dwarf, though a much lower mass white dwarf than those produced by sun-like stars. It will cool over an almost unimaginable timescale, gradually fading from white to yellow to red to brown to black. The cooling white dwarf will eventually reach thermal equilibrium with the cosmic microwave background radiation. At that point, it can cool no further. It becomes a black dwarf, a dark, cold remnant that will persist essentially forever, barring exotic processes like proton decay. When the last red dwarf dies and becomes a black dwarf, the stelliferous era officially ends. No stars remain. No fusion occurs anywhere in the universe. The age of light is over, and the age of darkness begins. This transition won't happen suddenly. It will be gradual, spread over trillions of years. The last 1,000 stars will fade one by one, each separated by perhaps billions of years. The universe will darken slowly, like a theater where the lights dim imperceptibly, until you're sitting in complete darkness without quite noticing when the transition occurred. And once that transition is complete, it's irreversible. No new stars will ever form. The matter that composed stars is now locked in stellar remnants or dispersed too thinly to ever collapse again. The universe will continue existing, time will continue passing, but the brilliant stelliferous era will be nothing but a distant memory encoded in the structures and remnants left behind. After the last star dies, the universe enters what cosmologists call the degenerate era. This era lasts from approximately 10 to the power of 14 years to 10 to the power of 40 years. That's 10 trillion years, a number so large that our minds cannot grasp it. During the degenerate era, the dominant objects in the universe are stellar remnants, white dwarfs, brown dwarfs, neutron stars, and black holes. No fusion occurs. No new energy is being generated except through gravitational processes and the gradual feeding of black holes. The universe is dark. The cosmic microwave background radiation, afterglow of the Big Bang, has cooled to almost absolute zero. Space is cold, empty, and mostly lifeless. But things still happen. Slowly. Very slowly. White dwarfs continue cooling. They radiate their residual heat into space, dimming over trillions of years. Eventually, they cool to the temperature of the cosmic microwave background and can radiate no further. They become black dwarfs, invisible chunks of degenerate matter drifting through space. Brown dwarfs, objects that never achieved fusion, also cool. They were already dim, barely glowing in infrared even when young. Now they fade entirely, becoming cold, dark objects distinguishable from planets only by their slightly higher mass. Planets, if any remain in orbit around the remnants of their parent stars, are frozen wastelands. No sunlight warms them. No geological activity persists after trillions of years of cooling. They're inert, dead worlds, some still orbiting invisible black dwarfs out of habit and momentum. Neutron stars, the collapsed cores of massive stars, also cool. They were never significant sources of light, but they radiated heat and sometimes magnetic energy. That gradually diminishes. They become cold, dark neutron stars, still incredibly dense and massive, but no longer emitting anything detectable. Black holes, paradoxically, are among the most active objects in the degenerate era. They consume any matter that falls into them, occasionally accreting enough to produce brief flares of radiation as the matter heats while spiraling inward. But such feeding events become increasingly rare as the universe's matter disperses. The primary process shaping the degenerate era is gravitational. Stellar remnants slowly interact through gravity. If two objects pass close enough, they can gravitationally scatter each other, altering their orbits. Over immense timescales, these interactions gradually reorganize the structure of galaxies. Some remnants are ejected from their galaxies entirely, flung into intergalactic space by gravitational interactions. They'll drift through the void forever, slowly cooling, never encountering anything else. Other remnants spiral inward toward the galactic center. This happens through a process called dynamical friction. As an object moves through a galaxy, it gravitationally attracts nearby objects, which speeds up behind it and slows it down. Over time, this saps the object's orbital energy, causing it to fall toward the center. Eventually, many remnants will accumulate near the galactic core. There, they'll interact more frequently. Some will merge. White dwarfs can collide and combine. Brown dwarfs can merge. Neutron stars can collide in spectacular events that release gravitational waves but no light. Since no one is around to see, these mergers occasionally produce interesting results. Two brown dwarfs combining might exceed the mass threshold for hydrogen fusion, creating a late-era red dwarf. This star would be born in a dead galaxy, surrounded by darkness, the only light source in trillions of miles. It would live for trillions of years, then die, and no other stars would replace it. Or two white dwarfs might merge and exceed the Chandrasekhar limit, the maximum mass a white dwarf can support against gravity. The result would be a Type Ia supernova, a brilliant explosion that would briefly illuminate the dead galaxy before fading. These events are rare, separated by billions or trillions of years, but time is plentiful in the degenerate era. Rare events eventually occur simply because there's so much time for them to happen. The most massive remnants will eventually sink to the galactic center and merge with the supermassive black hole there. Most galaxies contain supermassive black holes in their cores, millions or billions of times the sun's mass. These black holes will gradually consume nearby remnants, growing larger. But even black holes are not immortal. In 1974, Stephen Hawking discovered that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly faint for large black holes, but becomes more intense as the black hole shrinks. For stellar mass black holes, Hawking radiation is negligible. The time required for a black hole of one solar mass to evaporate completely through Hawking radiation is about 10 to the power of 67 years. That's far longer than the degenerate era. Supermassive black holes take even longer. A black hole with 1 billion solar masses would require 10 to the power of 100 years to evaporate. These timescales are so vast that they dwarf the entire degenerate era. So during the degenerate era, black holes grow by accretion faster than they shrink by evaporation. They're the ultimate survivors, the final major objects remaining in galaxies. By the end of the degenerate era, around 10 to the power of 40 years, most stellar remnants have either been ejected from their galaxies, merged with other remnants, or fallen into the central black hole. Galaxies consist primarily of a supermassive black hole surrounded by a diffuse halo of ejected remnants, all invisible, all cold, all essentially frozen in time. The universe at this point is unrecognizable. No stars, no planets with atmospheres or oceans, no complex structures except the remnants of long-dead stars and the black holes that consumed them. Space is cold, dark, and empty, and yet the universe continues. Time passes. The cosmos expands, but nothing changes. Or rather, changes occur so slowly that billions of years pass without any noticeable difference. This is the universe's future. Not a catastrophic ending, but a gradual fading into silence and darkness. A universe where the last star died trillions of years ago, and nothing remains but cooling remnants and patient black holes waiting out eternity. Now we reach the central question. What will the last star actually be? Can we identify its characteristics? Can we predict when and where it will form? The answer requires understanding which stars live the longest and which will still be forming when the universe's star-forming gas is nearly exhausted. Stellar lifetime is inversely related to mass. Massive stars live fast and die young. A star with 20 solar masses might last only 10 million years. A star with 10 solar masses might last 30 million years. Our Sun, at 1 solar mass, will last about 10 billion years total. Red dwarfs, with masses between 0.08 and 0.4 solar masses, can last trillions of years. The smallest red dwarfs, just barely massive enough to sustain fusion, might persist for 10 to 20 trillion years or more. These longevity estimates come from models of stellar structure and nuclear fusion rates. They're well tested for stars we can observe, but become more speculative for the smallest red dwarfs because none have had time to die yet. The universe is only 13.8 billion years old. Even the oldest, smallest red dwarfs are still shining. We've never seen one die. But the physics is well understood. Low-mass stars fuse hydrogen at a slow rate because their core temperatures and pressures are lower. They're fully convective, meaning material circulates throughout the star's volume, bringing fresh hydrogen to the core as fusion products are removed. This efficient mixing allows them to consume nearly all their hydrogen, not just the hydrogen in the core. In contrast, larger stars like our Sun are only partially convective. Hydrogen in the outer layers never reaches the core. When core hydrogen is exhausted, plenty of hydrogen remains in the outer layers, but it's inaccessible for fusion under normal conditions. The star transitions to red giant phase. Red dwarfs don't have this problem. They're fully mixed. Every hydrogen atom eventually participates in fusion. This extends their lifetimes dramatically. Based on current star formation rates and trends, we can make some predictions about the last star. First, it will almost certainly be a red dwarf. These are the longest-lived stars and the most common. They form in greater numbers than any other stellar type. When star formation is winding down and gas reserves are nearly exhausted, the few remaining gas clouds that do collapse will likely produce red dwarfs rather than larger stars. Second, it will probably be very small, perhaps 0.08 to 0.1 solar masses. This is close to the minimum mass for hydrogen fusion. Gas clouds in the late stelliferous era will be sparse and diffuse, struggling to accumulate enough mass to trigger fusion. The stars that do form will be on the small side. Third, it will form in a galaxy that still has residual star-forming gas. Most galaxies will have exhausted their reserves long before, but some galaxies, particularly smaller ones with lower star formation rates, might retain gas longer. Or perhaps a late-era galaxy merger will bring together two gas-poor galaxies, and the collision will compress their sparse gas enough to trigger one final burst of star formation. Fourth, it will form in relative isolation. By the time the last star forms, the universe will be dark and empty. Most stars will have died. Galaxies will be separated by ever-increasing distances due to cosmic expansion. The last star will shine alone, perhaps the only light source in its entire galaxy, illuminating nothing but darkness. The location is uncertain. It could be in a small dwarf galaxy that formed late and conserved its gas. It could be in a galaxy similar to the Milky Way that happened to have one remaining pocket of usable hydrogen. It could be in a galaxy we can't currently see because it hasn't formed yet. Remember, we're talking about events roughly 100 trillion years in the future. The current structure of the universe will be utterly transformed by then. Galaxies will have merged, dispersed, or been carried beyond cosmic horizons. Predicting which specific region will host the last star is impossible, but we can describe what that event will look like. Somewhere in a dark galaxy, a small cloud of cold hydrogen will be collapsing. It's one of the last such clouds in the universe. All around it, the galaxy is dead. Black dwarfs, neutron stars, black holes, all cold and dark. No light has shone here for trillions of years. The collapsing cloud fragments. Most fragments don't have enough mass to ignite fusion. They become brown dwarfs, objects too small to be stars. But one fragment, just barely, has enough mass. As it contracts, its core heats. Slowly, over millions of years, the temperature rises. The protostar begins to glow, first in infrared, then dimly in red. It's pulling in the last wisps of available hydrogen, growing incrementally. Finally, after perhaps 50 million years of contraction, the core temperature reaches 10 million degrees Celsius. Hydrogen nuclei begin fusing into helium. Energy floods outward. The pressure balances gravity. The collapse stops. The last star has been born. It shines with a deep red light, barely visible. Its surface temperature is perhaps 2,500 Kelvin, cooler than a candle flame. Its luminosity is less than 1,000th that of our Sun. If you stood on a planet orbiting this star at the distance Earth orbits the Sun, the star would appear as a dim red ember, providing barely enough light to see by. But it's fusion. It's a star. And it's the last one the universe will ever create. This star will burn for an incomprehensible length of time. Being so small and cool, its fusion rate is minimal. It will consume its hydrogen with extreme efficiency over perhaps 20 trillion years. During that entire period, it will be the only star shining in its galaxy, possibly the only star shining for billions of light years in any direction. What would it be like to witness this star? Imagine standing on a frozen world orbiting this final light source. Above you, the star glows dully, casting a faint reddish illumination across the landscape. The sky is completely black. No other stars are visible. They've all died. The cosmic microwave background is too cold to detect with the naked eye. You're surrounded by absolute darkness in all directions, except for this one feeble point of light. The silence would be total. No solar wind to speak of, no radio emissions, no particle radiation. Just the patient, steady glow of hydrogen fusing into helium deep in the star's core. Years pass, centuries, millennia, millions of years. The star's appearance doesn't change perceptibly. It continues shining at the same dim intensity, unchanging, eternal. But it's not truly eternal. Even this miserly fusion cannot continue forever. The hydrogen supply, though used efficiently, gradually depletes. After 10 trillion years, the star has consumed half its hydrogen. After 15 trillion years, 3/4 is gone. The fusion rate slows. The star dims almost imperceptibly. At 20 trillion years, the hydrogen is nearly exhausted. Fusion sputters. The star's core begins contracting again, trying to reach temperatures high enough to fuse helium. But it's too small. It cannot achieve the necessary conditions. Helium fusion requires temperatures of 100 million degrees Celsius. This tiny star's core will never get that hot. Fusion stops. The last nuclear fire in the universe flickers out. The star contracts slightly, heats briefly through gravitational compression, then begins its long, cooling phase. It transitions through blue dwarf stage, a brief period where it's slightly hotter and bluer than before, then settles into white dwarf cooling. For the next trillions of years, this white dwarf will cool. Its temperature drops from tens of thousands of degrees to thousands to hundreds. It fades from white to yellow to red to brown. Eventually, it reaches thermal equilibrium with the cosmic microwave background radiation, now just a fraction of a degree above absolute zero. The last star is now a black dwarf, cold, dark, invisible, a lump of degenerate matter drifting through space, no different from the billions of other black dwarfs that once were stars. The age of starlight has ended. The universe continues, but it is a universe of permanent darkness. After the last star dies, the universe is dominated by black holes. This period, lasting from approximately 10 to the power of 40 years to 10 to the power of 100 years, is called the black hole era. During this unimaginably long period, black holes are the primary remaining massive objects. White dwarfs, neutron stars, and other stellar remnants still exist, but they're cold, dark, and inert. Black holes, by contrast, remain active in certain ways. Black holes grow by accretion. Any matter that falls past their event horizon is consumed, adding to the black hole's mass. In the sparse, dark universe of the black hole era, accretion events are rare. Matter is thinly distributed, and most of it is in the form of cold stellar remnants that rarely encounter black holes. But occasionally, a black dwarf or neutron star's orbit decays enough that it falls into a black hole. The black hole grows incrementally. Over trillions of years, this slow feeding continues. Black holes in galactic centers gradually consume nearby remnants. Meanwhile, stellar mass black holes, the remnants of massive stars that died long ago, also persist. These black holes have masses ranging from a few to perhaps 100 solar masses. They drift through space, occasionally encountering other objects. If two stellar mass black holes pass close enough, they can gravitationally bind to each other, forming a binary system. Over time, the binary emits gravitational waves, losing energy. The two black holes spiral closer together. Eventually, they merge in a catastrophic collision that releases an enormous pulse of gravitational wave energy. This process takes an incredibly long time. A binary black hole system, with both members having 10 solar masses, separated by 1 light year, would take roughly 10 to the power of 27 years to merge through gravitational wave emission. That's far longer than the degenerate era, but still within the black hole era. When they merge, the result is a single larger black hole. No light is emitted, no radiation except gravitational waves, which ripple through space-time at light speed, carrying away energy. In the empty universe, these waves travel undetected, disturbing nothing. Supermassive black holes in galactic centers also persist. These monsters, millions or billions of solar masses, are the ultimate survivors. They've consumed much of their galaxy's matter over the degenerate era. Now they sit in near-empty space, occasionally accreting a stray black dwarf, or merging with stellar mass black holes that wander too close. Galaxies themselves, or what remains of them, slowly dissipate. Gravitational interactions over trillions of years eject most remnants into intergalactic space. Eventually, a galaxy consists of little more than a supermassive black hole surrounded by a diffuse cloud of ejected objects, all widely separated and barely interacting. Some galaxies undergo collisions even in the black hole era. Cosmic expansion has separated most galaxies beyond the point where they can interact, but within galaxy clusters, some mergers still occur. When two galaxies merge, their central supermassive black holes eventually spiral together and merge, creating an even larger supermassive black hole. The largest black holes in the universe, those with tens of billions of solar masses, formed through this process of repeated mergers over cosmic timescales. But even black holes are not truly eternal. Stephen Hawking's discovery of black hole evaporation through quantum radiation ensures that all black holes will eventually decay. Hawking radiation arises from quantum fluctuations near the event horizon. Virtual particle pairs constantly pop into existence throughout space, typically annihilating almost instantly. But near a black hole's event horizon, one particle can fall into the hole while the other escapes. To an outside observer, this appears as if the black hole is emitting radiation. The temperature of this radiation is inversely proportional to the black hole's mass. A stellar mass black hole has a Hawking temperature of about 1/10,000,000th of a degree above absolute zero. That's far colder than the cosmic microwave background, so the black hole actually absorbs more energy than it radiates. It grows rather than shrinks. But the cosmic microwave background cools as the universe expands. Eventually, it becomes colder than even a stellar mass black hole's Hawking temperature. At that point, the black hole begins losing more energy through Hawking radiation than it gains through absorption. It starts evaporating. For a black hole with 10 solar masses, evaporation takes approximately 10 to the power of 67 years. The black hole shrinks slowly at first. As it loses mass, its Hawking temperature increases and it radiates faster. The process accelerates. In the final stages, the black hole evaporates rapidly, its Hawking temperature soaring to billions of degrees. In its last moments, it releases a final burst of energy, then vanishes completely. Nothing remains. The mass and energy that comprised the black hole have been converted into radiation and dispersed into space. Supermassive black holes take far longer. A black hole with 1 billion solar masses requires about 10 to the power of 98 years to evaporate completely. A black hole with 10 billion solar masses requires 10 to the power of 100 years. These timescales are almost beyond comprehension. They dwarf the age of the universe by a factor so large it's meaningless to our human minds. But they are finite. Given enough time, all black holes evaporate. The black hole era ends when the last supermassive black hole completes its evaporation. This happens around 10 to the power of 100 years after the Big Bang, give or take several orders of magnitude, depending on the mass of the largest black holes. With the last black hole gone, nothing massive remains. No stars, no remnants, no black holes. Just the photons and low-mass particles produced by black hole evaporation spreading through an exponentially expanding universe. The universe enters its final age, the Dark Era, which will continue, essentially, forever. The Dark Era begins around 10 to the power of 100 years after the Big Bang and continues indefinitely. Some cosmologists suggest it might last until 10 to the power of 1,000 years or beyond. But the concept of time becomes increasingly abstract in this epoch. During the Dark Era, the universe is nearly empty. The density of matter and energy is so low that vast regions of space are completely devoid of particles. The average distance between particles is measured in light years or more. What exists in this dark universe? Primarily photons, the particles of light produced by black hole evaporation. These photons are incredibly low energy, their wavelengths stretched by cosmic expansion to sizes larger than galaxies. They carry almost no energy and interact with nothing. Neutrinos also persist, ghostly particles that barely interact with matter, even under normal conditions. In the Dark Era, they're spread so thinly that they essentially don't interact at all. Electrons and positrons, if any remain from black hole evaporation, drift through space. Over inconceivable timescales, they might occasionally encounter each other and annihilate, producing photons. But such events become rarer as the universe expands and particles spread further apart. If protons are stable, then black dwarfs and neutron stars still exist, cold and dark, composed of degenerate matter held up by quantum pressure. They'll persist essentially forever, unchanging relics from an age when matter was dense enough to form structures. But proton stability is uncertain. Some theories of particle physics predict that protons decay with a half-life around 10 to the power of 34 years. If true, then on timescales of 10 to the power of 40 years, most protons will have decayed. Black dwarfs and neutron stars will slowly evaporate as their constituent protons decay into lighter particles. This process is extraordinarily slow. A single black dwarf might take 10 to the power of 40 years to completely decay, but eventually, even these final remnants of the stelliferous era would vanish, leaving nothing but the decay products: positrons, electrons, neutrinos, and photons. If protons are stable, then black dwarfs persist forever, but they're irrelevant to the larger cosmos. They drift through expanding space, cold and dark, never encountering anything, effectively removed from any causal interaction with the rest of the universe. The universe in the dark era is approaching heat death, the state of maximum entropy, where all energy is evenly distributed and no work can be extracted. This is the ultimate fate predicted by thermodynamics. In a heat death universe, nothing happens. No stars shine because fusion requires concentration of matter. No black holes evaporate because they've all already evaporated. No particles interact because they're too dispersed. Temperature everywhere equals the background temperature, infinitesimally close to absolute zero. Time becomes meaningless in a heat death universe. If nothing changes, if no events occur, how do you measure time? Seconds, years, eons all become indistinguishable because there's no process to mark their passage. The universe continues existing, but in a state of perfect equilibrium. Space expands, but the expansion makes no difference. Particles drift apart, but they were already infinitely separated in any practical sense. The cosmos has reached its final configuration, and that configuration will persist forever. This is not the dramatic ending often imagined in science fiction. No big crunch where the universe collapses back to a singularity. No big rip where dark energy tears apart even atoms. Just a gradual, inexorable slide into cold, dark, unchanging equilibrium. Some find this depressing. The universe, once filled with stars and galaxies and possibility, reduced to a cold void where nothing happens and nothing can happen. All the beauty and complexity that once existed, from galaxies to stars to planets to life, erased and forgotten. But there's a certain peace in it as well. The universe doesn't end in violence or catastrophe. It simply becomes still. Like a pond that was once turbulent, settling into perfect calm. The motion stops, the ripples fade, and the surface becomes mirror smooth. And perhaps, in some sense, the universe is finally at rest. The enormous energies released in the Big Bang, which drove expansion and structure formation and stellar evolution for trillions of years, have finally dissipated. The cosmos has expended all its available energy and settled into the configuration demanded by thermodynamics. It's worth noting that these predictions assume current understanding of physics is correct. We don't know what dark energy actually is. We don't know if protons decay. We don't know if our cosmological models are complete. There could be unknown processes that change the universe's fate. Vacuum decay could spontaneously destroy the current vacuum state and replace it with something else. New particles or forces could become relevant at ultra-low energies. The laws of physics themselves might evolve over cosmic timescales. We're extrapolating our current knowledge across timescales that dwarf our experimental verification by factors of 10 to the power of 90 or more. That's a lot of room for unknowns. But based on what we do know, based on thermodynamics and general relativity and quantum mechanics as we currently understand them, the universe is headed for heat death. The last star will die, the last black hole will evaporate, and the cosmos will settle into eternal darkness and stillness. We've traced the universe from the first stars to the last star and beyond into the inconceivable darkness of the dark era. Now let's reflect on what this means. What does it tell us about existence, about our place in the cosmos, about the nature of time itself? The last star represents an ending. Not just the end of one star, but the end of an entire cosmic epoch. The Stelliferous Era, the age when the universe was bright with fusion and possibility, will conclude when that final red dwarf exhausts its fuel. Everything that came before, the billions of years of stellar evolution, the countless stars that shone and died, the galaxies that formed and merged, the planets that orbited and perhaps hosted life, all of it leads to that final moment when the last fusion reaction ceases and the age of stars ends forever. This gives the last star a certain poignancy. It's not special in any physical sense. It won't be particularly large or bright or unusual. It will be a small, dim, unremarkable red dwarf, probably indistinguishable from billions of red dwarfs that died before it. But it will be last. And that gives it significance beyond its physical properties. When it dies, something irreplaceable is lost. Not just one star, but the possibility of stars. The universe will transition to a state where stars cannot exist, and that state will persist forever. We humans have a tendency to think of endings as tragic. The last of anything carries emotional weight. The last passenger pigeon, the last fluent speaker of a dying language, the last member of an extinct species. These endings feel like losses, diminishments of the world's richness and diversity. The last star fits this pattern. When it dies, the universe becomes poorer in a sense. Light, which has shone since cosmic dawn, will be extinguished. The beauty of a stellar nursery, gas clouds illuminated by newborn stars, will never exist again. The warmth of a planet basking in its sun's light will become impossible. But there's another perspective. The universe doesn't care about stars. Stars are temporary structures arising from specific conditions, no more fundamental than waves on an ocean. The wave exists for a moment, then dissipates, and the ocean continues. The ocean doesn't mourn the wave. Stars exist because the universe, in its early epochs, had conditions that allowed them to form. High density, available hydrogen, gravity to pull gas together. When those conditions change, stars cease forming. This is natural, inevitable, no more tragic than winter following autumn. The universe doesn't end when the last star dies. It continues. Time passes, space expands, particles drift through the void. From the universe's perspective, if such a thing can be imagined, the Stelliferous Era is just one phase among many. It came after the Dark Ages and before the Degenerate Era. It was different from what came before and what comes after, but not inherently better or worse. Of course, we humans find the Stelliferous Era special because we exist during it. We are creatures of starlight. Our atoms were forged in stars. Our planet orbits a star. Our evolution was shaped by the energy our sun provides. We look up at night and see stars, beautiful points of light that inspire wonder and curiosity. It's natural for us to privilege this era, to see it as special because we're part of it. But we must recognize this is a selection bias. If conscious beings existed in the degenerate era, perhaps as exotic life forms adapted to the cold, dark cosmos, they might consider their era special for different reasons. The stability, the lack of radiation, the long timescales allowing for slow, patient processes. We can't know if such beings will exist. Current understanding suggests complex life requires energy gradients like those provided by stars. In the dark, cold universe after the Stelliferous Era, where does energy come from? How does metabolism work? How does evolution proceed? But we've been surprised before. Life on Earth exists in environments we once thought impossible. Thermal vents in deep oceans, frozen Antarctic lakes, deep underground in solid rock. Life is more resilient and adaptable than we expect. Perhaps in the distant future, some form of life will arise that doesn't depend on stars. Life that operates on timescales of billions of years, experiencing time so slowly that the eons we find incomprehensible feel like moments to them. Life that finds beauty and meaning in a dark universe we would consider dead. Or perhaps not. Perhaps the Stelliferous Era is unique in its ability to host complexity and consciousness. Perhaps when the last star dies, the universe truly does become lifeless and remains so forever. We don't know. We can't know. We can only observe the universe we inhabit, extrapolate its future based on physical laws, and accept that our time is limited, both as individuals and as a cosmic epoch. The last star, when it finally ignites, will not know it's the last. It will fuse hydrogen into helium, shine for trillions of years, and die, just like every star before it. There will be no ceremony, no recognition of its significance. It will simply be, and then not be. But in some sense, every star is the last star from its own perspective. Each star experiences its existence, shines for its allotted time, and ends. Whether it's the first star or the last star or one of the trillions in between, the experience is the same. Existence, then ending. We are, in our own way, like stars. We exist temporarily. We shine, in our own manner, contributing our light to the universe. We end. And whether we're among the first humans or the last, whether our species persists for millennia or millions of years, the pattern is the same. This cosmic perspective can be sobering. It reminds us of our insignificance, our transience, the vast scales of time and space that dwarf our brief existence. But it can also be liberating. If nothing lasts forever, if even stars die and the universe itself fades to darkness, then perhaps we're free to find meaning and beauty in the present moment, however fleeting. The last star will shine alone in a dark universe, its light illuminating nothing but empty space. Yet it will shine. For trillions of years, that fusion will continue. That energy will radiate outward, even if no one is there to see it. There's something defiant in that, something beautiful. Against the vastness and emptiness and inevitable ending, that star will burn, converting mass to energy, fighting entropy through fusion. And when it finally exhausts its fuel and dies, when the last fusion reaction completes and the last photon radiates away, the universe will be darker. But it will have had light. For a time, there were stars. That, perhaps, is enough. Our discussion so far has assumed the universe will continue expanding forever, driven by dark energy, eventually reaching heat death. But cosmology is an evolving science, and our understanding of the universe's fate might change. Let's explore alternative scenarios that could alter when and how the last star exists. Scenario 1. The Big Crunch. If dark energy doesn't exist, or if its effect reverses, the universe's expansion could slow, stop, and reverse. Gravity would pull everything back together in a process called the Big Crunch. In this scenario, the universe would contract. Galaxies would collide more frequently. The cosmic microwave background would heat up as space compressed. Eventually, all matter would collapse into a singularity similar to the Big Bang, but in reverse. How would this affect the last star? If the Big Crunch happens quickly, within trillions of years, then many red dwarfs formed during peak star formation would still be shining when the universe ends. There wouldn't be a clearly identifiable last star because the universe would end while stars still existed. If the Big Crunch is slower, happening after 100 trillion years or more, then the scenario plays out similarly to heat death until the contraction begins. The last star would form and die as previously described, but instead of eternal expansion and heat death, the universe would eventually recollapse. Current observations strongly suggest dark energy is real and the universe will not recollapse, making this scenario unlikely. But we cannot completely rule it out. Scenario 2. The Big Rip. If dark energy strengthens over time, cosmic expansion could accelerate beyond current rates. In an extreme case, called the Big Rip or cosmic doomsday, expansion would accelerate so much that it would eventually overcome all forces holding matter together. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems. Eventually, stars themselves would be ripped apart by the expanding space. Finally, atoms would disintegrate as expansion overpowered even nuclear forces. If the Big Rip occurs, the last star's fate would be strange. It might be ripped apart while still fusing hydrogen, its matter torn from it faster than it can be consumed by fusion. Or the accelerating expansion might prevent star formation altogether before the last star has a chance to form. Current measurements of dark energy suggest it's constant or very slowly changing, making a Big Rip unlikely on timescales shorter than hundreds of trillions of years. But again, we can't completely rule it out. Scenario 3. Vacuum decay. Quantum field theory suggests our universe might exist in a metastable vacuum state, like a ball resting in a valley that's not the lowest possible valley. If a lower energy state exists, quantum tunneling could spontaneously create a bubble of true vacuum that expands at light speed, destroying everything it touches. If vacuum decay occurs, it would happen without warning. The physics inside the bubble would be different, perhaps radically so. Atoms might not be stable. Fusion might not occur. The bubble would expand until it consumed the observable universe. This could happen at any time, tomorrow, in a billion years, or never. If it happens before the last star forms, then the last star never exists. If it happens after, the last star might be consumed mid-fusion, or it might evade the bubble if space has expanded enough that the bubble can't reach it. Vacuum decay is purely hypothetical. We have no evidence it's occurring or will occur, but the possibility exists in our theoretical models. Scenario 4. Cyclic universe. Some cosmological models propose the universe goes through cycles of expansion and contraction, or perhaps cycles of different vacuum states. Each cycle might last trillions of years, then transition to a new cycle with different physical constants. In a cyclic universe, the last star of one cycle would be followed eventually by new stars in the next cycle. Last becomes a relative term, applying only to one cycle rather than to all of existence. These models are speculative and not well supported by current evidence, but they represent possible alternatives to the heat death scenario. Scenario 5. Unknown physics. The most honest alternative scenario is simply, we don't know. Our understanding of physics is incomplete. Dark matter and dark energy, which comprise 95% of the universe, remain mysterious. We don't know what they are fundamentally. On timescales of trillions of years, unknown processes might become important. New physics might emerge at ultra-low energies or ultra-long distances. The laws of nature themselves might evolve or change. Predicting the universe's behavior across 100 trillion years based on physics we've tested for mere centuries is extraordinarily speculative. We're likely correct about broad trends, but details could surprise us. Perhaps stellar remnants can undergo exotic processes we haven't imagined, briefly reigniting fusion in ways that seem impossible with current knowledge. Perhaps quantum tunneling allows brown dwarfs to spontaneously. Subscribe to the channel for more science-related videos.